Continuing on with our discussion of reaction rates, in this video, I'm going to be covering how to solve for the order of a particular reactant and the overall order of a reaction. So if we're given the reaction A plus B goes to C, in order to solve for the order of these reactants and the overall order of a reaction, the first thing we need to do is write our rate law. So the rate of reaction is equal to little k times A times B. Now, one thing I left out in the last video is the order of our reactants. You need to include the order of your reactants every single time you write a rate law. So the order will be what these individual reactants are raised to as an exponent. So we do not know the order of A or the order of B yet. So I denoted them with arbitrary variables X and Y. So this will tell us the order of A and the order of B. Order of B. So what does this mean? What does the order of A and the order of B mean? So the order of a reactant will tell us really important information. It will tell us how changing, say we were trying to calculate the order of reactant A. The order would tell us how changing the concentration of A will change the overall reaction rate. So if we change the concentration of A, we need to see how that will affect the rate of the reaction. Once we determine how that works, we will know the order of A. We can do the same thing for B. And once we find the order of A and the order of B, all we need to do is add them together to find the overall order of the reaction. But before we can do that, we will find the individual order of A and the individual order of B. So in order to do this, you will look at some experimental data. So if we see A plus B goes to C, the first thing I would do to solve this, I would write my rate law, rate of reaction equals K times A raised to its order, we don't know it yet, and B raised to its order. I picked X and Y. That just means we don't know them yet. So if we want to use this data table to solve for the order of A and B, we need to pick two runs that can tell us something about how the concentration changes will affect the rate of reaction. So if we first want to look at A, what we need to do, like any science experiment, if you want to see how changing one thing changes another, we need to keep everything else constant. So we need to pick two runs. Basically, we ran this reaction 3 times and we measured the rate of reaction all 3 times. We need to pick 2 runs of this reaction where B's concentration stays the same. So we know that B is not the thing that is affecting our rate of reaction. So what we can do is pick runs 1 and runs 2 because we can see that B does not change. So what we do is we look at the concentration of A in runs 1 and runs 2, and we look how the rate changes. As we can see, doubling the concentration of A also doubled the rate of reaction. So the concentration of A went from 2 molar to 4 molar. This doubled. And the rate of reaction went from 1 times 10 to the -5th to 2 times 10 to the -5th, which also doubled. What this means is that A is first order. When you say that a reactant is first order, what you are saying is however you change the concentration of that reactant, the same change will be made to the rate of the reaction. So we doubled A, so the rate doubled. If we were to triple A, the rate would have tripled. Quadrupled A, the rate would have quadrupled. And if we halved A, the rate would have halved. So it is like a 1-to-1 ratio of change between changing the concentration and changing the rate. That is a first order reactant. So what we can do is we can fill in information in our rate law. We can say Ka, this is first order. We denote that with a 1. We still don't know B. So now we solve for the order of B. So what we can do is pick 2 runs. Let me erase some of this stuff so we can see 2 runs that will work. This was 1 molar and 1 molar. So what we need to do now is pick 2 runs where the concentration of A stays the same. So in runs 1 and runs 3, the concentration of A does not change. This is good because now we can see that changing B will be the reason that the rate changes. A had no effect on this rate changing. So we can see that B doubles from 1 to 2, and the rate quadruples from 1 times 10 to the negative 5th to 4 times 10 to the negative 5th. So what we can see is that the concentration of B went from 1 molar to 2 molar, so it doubled. And the rate went from 1 times 10 to the negative 5th to 4 times 10 to the negative 5th. And this was multiplied by a factor of 4. So what we would do is call B second order. When you say that a reactant is second order, what you are saying is if you were to double the concentration of that reactant, the rate would go up by that factor raised to the second power. So B doubled, so the rate went up by 2 raised to the second power, so it quadrupled. If we were to say B tripled, if B was multiplied by 3, the rate would be raised by 3 raised to the second power. So that would be a multiplication factor of 9. So the rate would go up by 9. If we were to say B quadrupled, the rate would go up by 4 raised to the factor of 2. So it would go up by a factor of 16. So that's what it means to be second order. It goes up by that factor raised to the second power. And that makes sense because what we will do is we will denote B second order by putting a 2 right there. So what we have done is shown ourselves that A is first order, B is second order, which means that in this overall reaction, the reaction is first order with respect to A and second order with respect to B, but the overall order of this reaction is 3. All we did was add 1 and 2. So this video went over the order of reactants and the overall order, which is just basically saying how changing the concentration affects the overall rate of reaction.